Okay, welcome back. So let's continue with chapter 2. So we were talking about system call versus API, and so far we've been using UNIX standard C library as an example of an API. Right. So now this would be a case where you have like a read function, which is actually lower level compared to your like fscanf, right, in standard I/O. So it has the calling API like this: int file descriptor, void, buff pointer, right, and then size t for the max number of bytes to read, and it could read fewer than that, and has a return value of 0 bytes or -1 if errors, or if it reads a certain number of bytes, that's the return value. And then there are these related calls. So open, close, reading, writing, right? And then they each has its own call signature. Now, if you do standard I/O, then you would actually be making system call. So most likely you do # include standard IO.h and you call printf. That's an easier interface, friendlier. Why? Because you just do printf and then pass a C-style string, which means it's null terminated. And you could have formatting. And that formatting is done not in system call. It's before system call, right? So so if it's printf, fprintf, then it scans the format string, sees % something, and then so what it does is it actually copies everything up to the % something. Then whatever % something goes off and does a convert into string, then goes and continues filling the buffer. So that conversion, string conversion, is done at the user level by the library function. That's not part of the system call. Ultimately, once it constructs a string, it figures out the length, then it translates into write. And if you see write, the API looks like this. That the file descriptor, well, who has the file descriptor? Well, that file handle. Remember when you do open this, you have some the capital file start, right? That's file handle. That FD is part of that record. And then the buffer, the standard library itself has some temporary space. Then it creates a buffer with a formatted output. Then it passes that, not your format string. It passes its own formatted buffer. Count, how does it get the count? Well, it actually has to go through the C-style string, find the null, then construct the count, and then passes it, right? So in printf, you don't have to pass the count, but somebody does it for you, okay? So that's an advantage to a higher level API like standard I/O. Why? Because you don't have to do the lower level thing. Let the API handle this for you. And then, in fact, multiple printfs may be combined into a single write to optimize for the performance. Okay, so now there are these popular APIs. So Windows 32 certainly one of the most popular, defined by Microsoft Windows for user interface, disk, I/O. Now, what about UNIX? Well, it turns out there's many variants of UNIX. It was initially done by AT&T Bell Labs, and then Berkeley people did their own, and then Stanford, they had the System 5, which is kind of UNIX, kind of not, and then a few other companies also did their UNIX, and then of course they got sued by AT&T, and then then either get bought up or went out of business, and there's a few others, and of course Linux, you know, right? That's a Unix clone. There's been other ones. Berkeley people who did BSD went and started out Sun Microsystems with 2 people from Stanford. What's the chance of that happening? But yeah, they did Sun Microsystems, which then did Sun OS, Solaris. In fact, our department's been using these machines until pretty recently. And these have been the workhorse behind a lot of these machines. And of course, FreeBSD, and then Carnegie Mellon did Mach-kernel, which also is a variant of Unix, but then it's microkernel based. And then that turned into macOS, iOS, and so forth. So these are Unix-based systems. But then everybody did it their own way. So if you wrote it, at least in the old days, if you wrote it for one variant of Unix, try to compile for another variant, sorry, that wouldn't work because their API is still a little different. Their system call is different. So that's where POSIX comes in. POSIX is a portable OS interface for Unix. So it is a standard defined on top of these OSs. So a Unix can implement a POSIX API. So that way, they then resolve the differences. So the calling interface differences get taken care of by this layer, POSIX layer. So pretty much all modern versions of Unix are POSIX compliant. And even if you're not Unix, you could still implement a POSIX API if you really want to. And then of course there's Java API, and Java, as you know, you assume you have Java bytecode, and then you can run on JVM, or you could do various VMs that can do just-in-time compiler, ahead-of-time compiler, which is what Android does. But these are really for a virtual machine. And ultimately, it has to go down to real system call, right? And so then there's mapping to the host OS. So, but doing Java API, one advantage is that it's another abstraction layer. So at least the vision was write once, run everywhere. So they just have to port the virtual machines to different OSs. Then the same API call then gets taken care of by the virtual machine, and then it calls the appropriate system calls on the different machines. So even if it's not POSIX compliant, it doesn't matter if it's Windows POSIX compliant, it'll work. Okay? So that's a different approach to these APIs. So API done certainly for various reasons: simplicity, portability, efficiency. So we touched on these different reasons. Simplicity, really they're designed for convenience of the programmer. You don't have to keep track of the length of your string, the language feature, right, the null termination or anything. That makes it much easier, less burden on the programmer, less likely to make mistakes. Portability, so you want to be able to take your source code, recompile for different architectures and run. And so having some standard API like POSIX certainly is very helpful. Efficiency I talked about, so like the API layer can consolidate multiple API calls before making the actual system call, right? So like disk or IO example. So until you hit return, otherwise it doesn't flush. That's one example of optimization it can do. Not having to trap to OS can save you overhead, so that's nice. Okay, so here's some quick points. Different communication models, message passing, shared memories, and you can see review questions that will be posted later. Relationship between API, system call, C library, so why you want to use API instead of system call, should be able to answer that. Okay, now system programs. So we're going up a level now. So, in execution, the system call is that interface, the calling interface, the actual execution. But system programs, on the other hand, are more like these executable programs. You may be able to invoke from the command line, or maybe something that's called by OS or by other programs, maybe as a plugin, maybe as something else, really to help the OS operate. And to most users, the system programs is really their view of the OS, right? And of course, these include a lot of the same categories. So I gave Chion as one example last hour. It's the same name or very similar name between what you see in the system call and what you can type from the command line. Right? And there may be different versions of this, but they're just accessed from different places. One is for the program to call. That would be a system call or be API call. The other, here we're talking about system program. That's for you, perhaps you to type in from the shell as an executable program, which then makes that system call for you, okay? So handling file system status information, but additionally could handle more programming language level things. And so that's potentially what a loader does, loading, execution, cleaning up. communication, background service, application programs. Okay, so again, you see very familiar things, but these would be higher level. So create, delete, copy, rename, print, dump, list, right? So you can probably imagine, create, that's like touch or a lot of other Unix commands using. Delete, RM, copy, CP, rename, MV, right? Print, echo, or cat, or something, right? So you can probably do a rough mapping between these commands or system programs to the API call, or possibly even to these. So now, as a program, it doesn't have to be as primitive, right? It can do a lot more things because a program can be arbitrarily large or small. So a program like CP, for example, to copy, it's not just copying. It actually can do like additional checking, right? So does the file exist? Do you want to override it, right? It can do these additional, more user-friendlier things, checking for you. In fact, you could even add a file dialog, graphical user interface, right? It could do any one of those things. So we're talking about system programs here. Of course, their function is to provide really the user side calling interface, so to speak, or command interface to what otherwise might be one or maybe more system calls. Status information, get time available memory disk space, this quota, number of users, who's logged in, right? Debugging information, registry, that's more for Windows. And you can have higher level programs which otherwise would not be system calls. So your file search, your text editor, maybe content-based search like grep, transform text, right? So some of these may not be system call, but they're useful for supporting system operation. Programming language support, compiler, assembler, debugger, interpreters, and various things. Linker, loader, debugger, assembler. Communication, again, can be done at the higher levels. Why? Because it's not just about discovering what service is available, setting up. You can do higher level protocols. Because these interfaces would be rather low level, but then you can add higher level protocol on top. So it's not just opening up a socket or connection with another process or another host. Now you can do different types of service. Is it FTP? Is it HTTP? Is it SSH? Is it what? Right? Any one of those things. So these can be layered on top and more targeted to certain applications. Send email, right? They're done with the same similar set of primitives, but higher level they do more processing or formatting or other things to build up user level services. Okay. Background services, they're considered system programs as well, because there are things you might want to do for administration purpose, or just really to provide a good user experience. So like what do you run on startup, what do you run on periodically, like for example your backup process, or sometimes error checking, sometimes like defragmentation, right? Things like those. And even printing can be done as a background service. And ultimately, you have these bundled application programs, right? That's when you start to get into the gray area where is it really part of OS or is it application, or do you consider it part of system program even? Okay. Now, ABI is application binary interface. This is a term you can find in the textbook as well. And that is the definition of the executable program. So these executable programs actually come in different formats. So just because you compile to x86 or to ARM, to 8051, doesn't mean an OS can just run it, because OS does have certain format requirement or expectations. So if you CC and then run something, it could be in different formats. Like ELF is one that's pretty common. COF, common object file format. MacOF or Mac, and then Windows you can probably expect EXE, and then there's other ones too. And it's not necessarily just for one instruction set architecture. there's also what's called fat binary. So that's been done a lot for various architectures, especially like Apple has done a lot of these fat binary when they transition 2 times in their ISA. First from 68,000 architecture to PowerPC architecture, then to the x86 architecture. So it on the outside looks like one binary, but really it's a folder or it's a directory which contains the different binaries for different executables. And the loader knows which architecture is running and may call an emulator, may call a just-in-time compiler or something to do the translation and run properly. Okay, and also it's the same executable you can actually distribute to different machines. And these also include the more implicit one. Also, the explicit ones would have the header and maybe the symbol table. Like for debugging, you probably, it's maybe a little more painful to debug without the symbols in binary, but then you get to have some fun with just debugging with the binary addresses. And that having symbol table, that could be part of these the file formats too. Just so in case your program crashes, it actually can know which function in which it crashes in. But what's more implicit would be things like the stack convention, register convention, because certain registers may be used for certain purposes. And those would have to be part of that you might call protocol or convention that the executable and OS both have to agree on. And data types like sizes and endians, right? So like int, is int 16-bit, 32-bit, 64-bit? How big is int? Float, how big is float? And also you probably know about endian, right? So big endian, little endian, bit order, byte order. I mean, Intel tends to be little endian, byte order, so least significant byte in the lower address, but pretty much everybody else is big endian. But then there are architectures that support both. And so is the architecture compatible with itself, right? So that's kind of an issue. And so then also all these tools involved, including the linker that may do static linking or dynamic linking. If it does dynamic linking, how does it resolve the addresses and symbols, right? And loader, well, which is it, dynamic loading. So that means after your program starts running, it may load or unload parts of it. Okay, so let's look at some system structures. And now these people came up with different system structures just because there's different goals over time. Overall, it should be easy to use and learn, but it should be reliable, safe, fast. It wasn't always met, but then people try. And they are done with different constraints too, because processors used to be slow, memory used to be expensive, right? And you didn't have that much disk space either. And now, so for user, they have their perceived function of what they expect from the OS. Now for system designer or OS developer, there's different goals too. Because you don't just do OS once. I mean, yeah, some of you may do your project in this course as the last OS you ever write, but others may continue on and get a career in actually writing OS for some company, right? And so if that's what you want to do, then you want an OS that's easy to design, implement, maintain. Maintenance is important. And first, you want your OS to be reliable, error-free, and efficient. Efficiency is important, right? Because otherwise, the OS takes up all the resources, and it ends up being a bad user experience. So one important consideration is probably one of the most important things you should take away from this course is the separation of policy and mechanism in OS design, and in fact, in a lot of other designs too. So policy is what, whereas mechanism is how, right? What will be done, what's allowed to be done, right? Is one user allowed to access some other user's file, right? That's kind of a policy. Mechanism is, do you provide permission bits or different address spaces or what? Login, different user ID, and those would be the mechanisms. And what you want is have this clean enough separation so that you want to allow maximum flexibility. In case you want to change a policy, right? So you don't want to hardwire a particular mechanism or a particular policy with your implementation mechanism, so that later it's going to be very hard to change. So you always design, think what's policy or what can be considered policy, separate out as a parameter, so that your mechanism just focuses on what it does, and then later policy can be changed independently or mostly independently. It's not always separated so cleanly in commercial OSs, especially like DOS and Windows. They just needed something that was running, and they didn't have such clean separation. But over time, people learned and learn about the importance of separation between policy and mechanism, because that's what makes your OS maintainable. Okay, so let's look at case studies for a few OSs. Simple structure is like MS-DOS. That was done in the days of 640 kilobytes is considered a lot. It's probably it's like whoever needs more than 640 kilobytes of RAM, right? So it was designed for something much smaller, right? And so it's for minimum structure. So you have ROM booting up, so that's BIOS, right? It loads the basic things to load in the OS. And the OS itself, so the ROM or BIOS doesn't count as OS because it gets out of the way. And then MS-DOS gets loaded. And then there's some resident system functionality in there. Then it provides you with a shell, okay? And then from there, you can launch one application program at a time. So one program, and then when that program is running, OS actually covers or writes over part of the resident program, and then or part of DOS, and then when it's done, returns control back to DOS, and then you can do the next program. And so that's very simple structure, minimum structure, and then not really divided into module. Everything just mushed together. That the block diagram here drawn just really for conceptual purpose, but in the code it's not organized like that at all. And it's definitely unsafe. If you have a program crash, the whole system goes there. And in fact, that was the case even throughout much of Windows for the first decade. You get this blue screen of death, right? You see that all the time. Or I remember, like, you walk into the elevator and then see not the running ads, but then you see the blue screen, right? So that took a long time for them to fix. Certainly unsafe, and a lot of viruses could attack. Difficult to enhance too, and so they had to restart Windows many times. They got to a certain point, this is not maintainable. Throw it away, start over. They did it a few times. Okay, so this is single tasking. The shell is invoked after you boot up, and so MS-DOS. It's tightly integrated with the kernel, and when it runs, basically that user program replaces most, if not all, of the shell. So it doesn't really create a separate process. It just loads it, covers over, and when it finishes, it returns, and then the shell gets reloaded again. Right? And so that's a very simple structure. Now, and then a few years later, I mean, they did it because initial 8086 actually didn't offer user mode versus kernel mode. It wasn't until 386 that became the main selling feature. You could actually start protecting it, but OS still didn't really take full advantage until much later. And but at least that was a step in the right direction. So the separation between user mode, kernel mode at least allows the OS to run in one address space, separate from the user mode, right? So user mode could still crash, but at least OS wouldn't get trashed, right? So that helps, but I mean only to a certain extent, depending on how you write the OS. Certainly Unix from the very beginning took advantage of this because Unix was developed for initially PDP-11 and then the VAX. They supported the dual mode operation, but PCs didn't have that until much later. And so traditional Unix was done in this kind of two-layer or what's called monolithic structure. So user mode versus kernel mode. But the issue here with what's called monolithic is that in kernel mode, they actually didn't have a nice structure. It's all mushed in. It's one giant thing. And all the OSs get lumped in, right? And so it was okay at the beginning, relatively simple, and then as you add more features, and then people finding it, harder and harder to compile. And what if you have a bug in the OS, in the new feature you added? You still crash it, right? Because it's not user code that's crashing you. It's the OS, you're working on the OS with somebody else, and then they might be someone new that joined the team, and then if they have a bug, it crashes the entire OS. So even though it protects you from user bugs, it doesn't protect you from OS bugs, right? And so it makes it difficult to scale to larger complexity and having a robust version. Now Linux still follows this monolithic structure, but they made a change. They made it more modular. So yes, so technically you can say it's everything in Linux still runs in that same address space. That's what monolithic means. But at least it's more structured, and it's actually made more dynamically loadable. So you can dynamically load in modules as needed, and if not, unload. That's okay. And Windows evolved. I mean, Windows is not all the same. It evolved over time, and eventually they think, hey, Linux has a nice idea. Okay, we'll follow that. But Windows actually went through different structures as well. For a while, they went to microkernel as well, but then microkernel had its issues, so they eventually settled for something like that's Linux-like, also monolithic but modular. So this is the traditional two-layer Unix structure, monolithic kernel. So bottom, again, hardware, interface to hardware, and then all the services like signal handling, character I/O, file system, swap space, disk. Everything is one giant program, one giant OS program, so to speak, right? No structure to it, just a bunch of API all in there, right? And the calling interface, right? So yeah, you can have user program crashes. That's not going to trash another user program, but doesn't trash the kernel. But then if the kernel has bug, then this whole system goes down, right? Now, because of that, people started thinking, hey, is there an alternative? Can I protect OS somehow, right? This is really from OS developers' point of view. So they think, how about layer structure in OS? So hardware, and then maybe process allocation, multiprogramming, and then on top of that, you have memory management. So if you want to add new features, you're not likely to add it to the bottom layer. You only call down, and if you add a higher layer, at least you're not going to crash the lower layer, which remains robust, right? But then the problem there is each time you have to call down, maybe do you need hardware support for changing this layer? I mean, is it just kernel mode versus user mode, or there's different layers of kernel mode needed, right? I mean, that's a question. And if you don't, then how do you ensure that you don't overwrite anything that's implemented at a lower level layer? So this layer structure raises probably more questions than it answers, but it did become the model for your protocol stack, right? Remember, your TCP/IP actually is a layer stack, right? So, yeah, and then there's other things. So it's not entire OS, but that idea of making changes mostly at the higher level and not change the lower level, that keeps things more or less robust that way. Okay, so that did get manifested in most typical example is protocol stack. But then as an OS, it's really not done as much just because it raises more questions. So it may be easier for debugging maintenance, but it's actually less efficient because somebody has to maintain or enforce the concept of layers, right? Very much analogous to switching between user mode, kernel mode, but then now this processor has to maintain. I mean, just how many layers is enough? I don't know. And then each time you go down, you have to protect it somehow, protect more, right? I mean, to what level do you protect, right? So that's when some people came up with a microkernel idea. So most known example is macOS from Carnegie Mellon. So Mac is you might say Unix-like, or maybe Unix-based OS, but structured differently. What's the idea? The idea is, well, I don't really want one part of my OS to crash another part of OS. So what do? Well, same idea that I do user protection, right? I don't want one user program to crash another user program. So what do? Well, do I really need to do that OS service in kernel mode, or can I move it to a different user mode, right? And doing it user mode doesn't mean it's actually an actual user. It's just that the mechanism is just like another user process, except that user is a kernel-defined user. So it's not a real person that's using it. It's just OS just creates, okay, I'm making up a fake user. All it does is this service, right? So that means unless it's just a core service, which has to be done in kernel mode, everything else, if it doesn't have to be done in kernel mode, do it in a separate user's process, in its own user space. That gives you the protection, right? So that way, if that crashes, it's just like another user process, it doesn't crash the OS, right? So as you can see, the kernel itself is microkernel. It handles things like the network driver, device driver, graphics driver, going to the hardware side. But all it has to do with just a number of simple operations, maybe memory management, interprocess communication, and CPU scheduling. Those are the three things. Everything else is done outside the kernel, even if they look like traditional service. But yes, you do still make system call into the OS, but then OS does a few things, sets up the process and say, hey, okay, I'm going to route this to this other user process that does that system service for me. You can see it as it's a much more modular structure, yes. And so this is really the microkernel structure. So the core part, kernel, just has interprocess communication, memory management, CPU. That's all. Everything else, your file system, device driver, application program, done in user mode. But not just any user, just kernel-defined users, okay? Because nobody else gets to do those things. And they all have to make a system call, then the system routes them to the appropriate user level process. So this is an example of separation between policy and mechanism. This is using user mode mechanism, but then still retaining the policy of the protection, right? So protected access. So still you make system call into OS, but instead of doing the device driver file system in kernel, you do it in user space. And because they are separated out, any crash will not crash the OS. All right, so that's the microkernel structure. Certainly a nice idea and has certain advantages. Why? Because to do an OS, you just have to port that microkernel, which is limited in functionality. Code is not very big. You can get that debugged and running much more quickly, as opposed to a giant thing with everything in there. Compile takes it forever. You can dynamically hook up these things, add them over time, even as you're running. So if you want to add new driver, sure, you don't have to reboot the system. System keeps running. It just hooks them up over time, right? And you can even change it, right? And so it's much easier for porting. So certainly developers like to do this, right? It's more secure, more protected. but you pay a price. What kind of price? Well, as you can imagine, mode switching, right? Because you just switch from user mode to kernel to request a service. And then what does it do? It routes you back to another user that it creates, right? That's another mode switch, right? And switching back and forth. And then the worst part is what's called message passing. Why? Because it wants to protect these processes from each other. So message passing means what? It means it has to do copying. I want to send you a message. I can't just write to your memories. I have to give a buffer, you copy, or somebody copies it, and then they're detached from each other. And then to send to somebody else, another copy. You're copying all the time. That's wasted cycles. Whereas shared memory, you write to this buffer, pass the pointer, somebody reads from that same pointer, right? That's much easier. And so monolithic structures have that advantage. You don't have to do so much copying. You just share memory. But that's also what makes it so less secure, because what if you trash that buffer? Then the other person gets the corrupted one too, right? So right, so microkernel does pay the overhead of the copying as part of its protection, right? Because if you don't do the copying, you share memory, then that kind of defeats the purpose of the protection, right? So because that was developed at the time when PCs were still in 386 Pentium, not even Pentium, 486, still kind of slow, and they weren't exactly that. So Linux, Torvalds, who developed Linux, he was pretty adamant about doing monolithic kernel. So even to this day, it's still monolithic. That doesn't mean nobody did microkernel Linux. So Apple, actually, before they moved to PowerPC, they did an MK Linux, which is a microkernel version Linux. Why? Because they did Mach, and microkernel was all in Mach, and so that was a natural thing to do. They did a version of that, but that went around for a little while, and now it's back to monolithic, but it's a more structured monolithic. So that's called a modular structure. Now, Windows went through different phases. So Windows, for a while, they were doing NT. NT was a collaboration between digital equipment and Microsoft. And so Microsoft did a bunch of these collaborations. They first did DOS and kept the rights. So IBM never controlled DOS. And then IBM wanted to get some, and then Microsoft, when they saw Apple, okay, they got collaborating with Apple and then tried to copy from Apple in the meantime. And then they saw the IBM saw Windows and IBM wanted to do their own Windows called OS2. And so Microsoft said, okay, let's work together. But then Microsoft controlled these Office apps, right? So they intentionally make a few things incompatible using unpublished APIs. So when somebody runs OS2 to run their Office app, and they would crash randomly, and people start spreading rumor, oh, OS2 is not so good, it's incompatible, and then people kind of scared, even though OS2 was really advanced and it was protecting when Windows was crashing all over. So, and then, okay, anyway, so that's a separate, they learned from that experience and how to improve their OS. And then digital at the time, they were selling big workstations, and then they said, we gotta get Windows running on our workstations too. So, and digital was much better at OSs than Microsoft. And Microsoft really wanted to resolve their problem of crashing. So they said, okay, let's do Windows NT. NT stands for network technology or something. Basically, it was supposed to run on digital machines. These were alpha processors. It was the fastest in those days, probably 5 to 10 times faster than anything else out there. And then, digital learned about this from Mach, and then say, okay, let's do microkernel. Microsoft, okay. Then they did the API first. No, they were really just trying to learn from digital. They never really want to support digital. They just want to do PC. And then so eventually digital went out of business and Microsoft continued with NT. And NT, of course, was very different from the other Windows 95, 98, even ME. And then they tried to do something, eventually trying to merge the two back. So NT was really for a different class of PCs. And then eventually Microsoft XP actually was using a lot of the NT technologies. So that XP was probably the first version that didn't crash as much. And but then when they went from NT to XP, they actually backed off somewhat on the microkernel side, just because XP had to run on much lower end processors. So it became more monolithic, just for performance reason. And so how did monolithic kernel come back in fashion again? Well, so it was really with the idea of loadable kernel modules. So now kernel is really the core component plus these loadable kernel modules. So the idea is you want to keep just the core components, and then the other ones are not kind of compiled in or not hardwired in. You have the stub interfaces. So that means there's API there, but then behind there's really no code loaded by default, or unless you want to load it in. And so what happens if somebody calls that function that's not loaded? Well, it's a stub routine, and stub routine is not just returned right away. It actually triggers a loading function. Then it loads that particular loadable module into the OS. Okay, then it adds that functionality. And if you don't need it, unload it. Okay, so what are examples? So USB device driver could be an example, or you have other things that it's not essential, then don't put it in, right? So it does have certain advantages of microkernel in the sense that it does have that structure compared to the traditional Unix, which has really no structure. So it's enforced with this. So you pay a little bit of overhead loading, unloading modules as needed, but then you don't need to recompile. Because why? Because that loading interface is fixed, or more or less fixed, okay? And so you don't need to recompile. You just change your loadable module. But it has to agree to that interface. It's much lower overhead in execution. Why? Because it doesn't have to switch between kernel mode, user mode, backend, and it can take advantage of shared memory communication. Doesn't have to do message passing, which is a lot of copying. Okay, so this is the structure that's mostly converged now, and most modern OSs are this way: Solaris, Linux, Windows, and so forth. I mean, this is not an absolute classification. These are all like on a grayscale. Okay, so Solaris works like this. There's the core Solaris, and then there's different modules, and then these are dynamically loadable. So that way the system is up and running, and then it spreads out the overhead over time. Okay, so it can also be a good use of the resources, keeps the kernel stable and efficient. Most OSs are really some hybrid. Okay, so it's not just one single structure. The hybrid to address performance, security needs, and then so most are either monolithic plus loadable or microkernel plus layer plus loadable. So even microkernels can have loadable things too. So that makes them slightly more monolithic, but I mean, these are just two ends of the spectrum. Okay, so so the examples here: Linux, Solaris are monolithic plus dynamic loading, modular for dynamic loading. Windows is monolithic plus what's called microkernel for subsystem personalities, whatever that means. But I'm not going to test you on this. You can read the textbook if you want to find out more about this. Because there's just so many versions of Windows, it's like, okay, fine. If you're interested, read more, but it's not a core idea. Now, macOS, iOS, these are based on the Darwin kernel, and it's based on mock kernel plus a BSD Unix with a POSIX layer. So still Unix is a hybrid, and that means what that means is their mock kernel may be a microkernel, but that mock kernel actually can load in additional things, including IOKit kernel extensions. And of course, you can do things in user space as well. Android has Linux kernel, but then upper parts is layered or somewhat layered. Okay. So Darwin, so macOS, iOS looks like this. I mean, textbook has a similar drawing. So mock is microkernel, but then you can extend it. So beyond just scheduling IPC and memory management. And then you have the mock side and BSD side. Mock side does a certain set of system calls. So specifically scheduling IPC memory and plus a remote procedure called RPC. The BSD Unix side handles all the other ones. So like your command line interface, file system, networking, basically things you would normally do in the user space. Okay. But that's POSIX compliant, so that means you can write code, compile for this, and it'll run just like another Unix. And then on top you have library and then applications. So that was just the mock layer, which is the bottom box. What about Mac OS and this is Darwin. Now Darwin is just the bottom box. That's the kernel environment, right? And then macOS, iOS are stuff on top that then based on Darwin kernel environment. So you have core framework, application framework, user experience, and then application. But it's not a layered or strictly layered one because with the layer one, you can only call the next layer and then that calls down and calls down. This allows you to bypass and call down to a lower layer. Okay. Android, just a little background. Well, you probably heard of Android through Google, right? You think it's a Google thing. Well, it wasn't a Google thing at first. It was Android Inc. as a separate company. Initially, they were targeting these feature phones, so keyboards like a BlackBerry type, no touch screen. And it wasn't until they saw iPhone. Wow, this is cool. And okay, we got to go back into a drawing board. So they threw away most of their stuff and then restarted. And then they added touchscreen, and then they thought the only way to do this was to open source, big part of it. Okay, then so they did. But they were based on Linux kernel, but they made major changes to support power management, which is important for handheld devices. And then they added on top a lot of these things, Google Mobile Service. So that's what so that part is not open source. And Google Play, Google Mobile Services. And so it's a mixed license model. So part of it open source, the other part not open source. And each vendor can add its own thing to there. And so it's been ported to phones, TVs, even watches. Okay. So, and as you may know, Android apps, most likely you write in Java, although they're kind of switching away from Java because they get sued by Oracle, which owns Java. And so they, I think, consider Swift, which was used by Apple, and they have another language for it. But still, most developers still write in Java. So that means Java support is there. But it's not your traditional Java. Java has its own API, right? But this here, no, Java is just a language. And you don't call the traditional Java API. That's why Oracle is suing them. Hey, you're using Java. Why aren't you using our API, right? And they replaced it with their own API, right? So that's why Oracle is upset. You should be using because if you use somebody's API, they're in control, right? And so they bypass the control. So that's why Google gets sued by Oracle. And anyway, so then they do optimizations. Then compile to because bytecode is slow to interpret, so they do translation maybe ahead of time, and then they call their own framework for WebKit, SQLite, multimedia, and all those. So hardware, monolithic Linux kernel modified, and then they have this bionic layer which replaces standard C library with their own. And so that's another way for Google to bypass GNU control, because if you use the standard glibc, then it's GPL. GNU can then sue them. And then They just replace that layer. So it's not entirely compatible. That means if you have something that from Unix environment or Linux, you compile. Oh, sorry, there's no glibc, so it's not gonna run here. But Google doesn't care. Then HAL is for hardware abstraction layer, and you have native libraries, and above there's VM for ahead of time compile, and then Java native interface, Android framework application. So it's kind of a funny layered structure with a lot of support for Java bytecode execution and things, but then it's really not tied to Java, strictly speaking, because the calling interfaces, as long as they can create another substitute for it, can access exactly those same calls, same API, same system calls. Okay. So for supporting debugging, well, you need several things. One is to find fix error. So to find error, you need support for dumping out the error message, right? So there's logs and core dumps. And core dump, I don't know if you see much of that anymore, but I remember we were doing our assignments on shared Unix machine, and if your program crashes, segmentation file core dumped, and you get a core file. Now I don't think that's still the case, but if you use GDB, it can read from some dump file. So core dump is a memory content dump by the OS when the program crashes. Okay, and why would you need that? Because a debugger can go back and read that file and read the memory content, map it back to the source and addresses, and see where it crashed. Then let you look at the memory content post-mortem. Now, what if the OS crashes? Well, there's support for that too. This is called crash dump as opposed to core dump. And as an OS developer, you probably should look at your crash dump for that purpose. Similar idea, but then it's for OS stuff. Performance monitoring lets you do the tracing, the listing, the profiling, so you can get statistics on how your program is spending time or how OS is spending its time. So there's different tools for this, really just to help you improve your system, remove bottlenecks, know where the bottlenecks are. So in Unix, top, the program called top is if you haven't tried it, try it. And there's graphical versions of top, and then Windows has the task manager, which has the plot for the load, the CPU usage, disk usage, networking usage, and all that. Okay? So these are tools that need OS to get you access. And then you can monitor at per process level or system-wide level. There's all these tools you can use. So I'm not going to go into detail. Tracing, you can do tracing of system call using strace. GDB is a source level debugger. Now, it itself is not really strictly speaking a system program, but it helps. And perf is the Linux tool suite that includes stat, top, record, report, annotate, get list, and TCB dump with the to trace network packets. Okay, so that's chapter 2, and you can read the textbook just for additional information. Now, we will post review questions in the next couple of days, and next time we'll do more EdSim 51.